This meeting is being recorded.
Okay. Hello, sir. Our group is from 241 to 246, and the topic of our presentation is RTT theorem and impact of jets. So, uh, we will start with our first roll number, my first fellow, Samarth Sachdeva, whose roll number is 241. He is going to explain the RTT theorem. Samarth,
All
the
right.
word to you.
Uh, Thank you, Sanyam. Good evening, sir. So moving forward with RTT. So most principles of fluid mechanics are adopted from solid mechanics, where the physical laws dealing with the time rates of change of extensive properties are expressed for systems, right? So in fluid mechanics, it is usually more convenient to work with control volumes, and thus there is a need to relate the changes in a control volume to the changes in a system. The relationship between the time rates of change of an extensive property for a system and for a control volume is expressed by the Reynolds transportation theorem. So RTT, basically the Reynolds transport theorem, is named after the English engineer Osborne Reynolds, who did much to advance in its application in fluid mechanics. So here you can see the equation that is used to follow the Reynolds transport theorem, right? So moving forward, as we can see in the first law of thermodynamics, the laws in their basic forms are stated in terms of a system, a collection of matter, fixed identity. Basically, it can be, let's say, co-atoms or molecules. They basically contain the same mass no matter moves and interacts with the surroundings, right? So, system approach is not very suitable for the applications in fluid mesh because it's very hard to identify and track a group of fluid since it moves quite, let's say, randomly, right? So control volume approach is more often used in fluid mesh. Moving forward to how do we choose a control volume? So control volume, or as referred to as CD, it is an arbitrary shape which can be chosen by fluid dynamicists. However, selection of a CD can either simplify or complicate analysis, right? So clearly defining all the boundaries, analysis is often simplified if the control system is normal to the flow direction. So only control system conditions needed. You do not require detailed information inside the control volume. Therefore, if we can clearly identify all the fluxes crossing the control system, we can clearly identify the forces and torques of interest acting on the control volume and control system. So with this, this was the basic introduction of the Reynolds transfer theorem. Now I would like to pass it on to my fellow peer here, Sambhav.
Hello everyone. So my part start from derivation of Reynolds transportation theorem. So basically, what Reynolds transportation say? So like it deals with the intensive and extensive property of the control volume. So as it's shown in the second row, second line, like the property uh, system property of control volume system property is equals to property of control volume is equals to change in influx plus change in outflux, and here it is shown like rate of change of property system property with time equals to rate of change of control volume with time, like plus flux out minus flux in. Moving to next slide. uh, Here in this slide, like the time rate of change of the property B of the system is equal to the time rate of change of B of the control volume plus the net flux of B out of the control volume by mass crossing the control surface. So as it written over here, it is clearly stated like that uh, net flux equals to flux out minus flux in equals to like integral of control surface. Here is a row b dot b into n dot da. Inflow is negative only if like outflow is more than inflow, like outflow from the control volume rather than in entering the fluid. And one more thing, mentioning over here, like if something is entering in the control volume, we have to take it positive. Sorry, I correct myself. something is entering is we have to take it as negative, and something is going outward from the control volume is taken as positive. Moving to next slide. Here, like the property of the control volume equals to integral of control volume into rho into b dot d. Therefore, the system to control volume transformation for a fixed control volume equals to property of system rate of change of property of system equals to d upon dx integral of control volume plus integral of control surface. Moving to next slide. Over on this slide, the material derivative differential analysis of the system property is shown. General RTT not fixed CV integral analysis, like if our say control volume is not fixed, then we have to take an our second equation. Here in this table, like extensive property, what is extensive property? Extensive property are those property which depends upon amount, and intensive properties which depend upon the sample. uh, Sam, what is sample, and extensive is basically what is amount of the sample. So like if we like take the mass as a extensive property, then our intensive property in the equation is 1. And if we like take the momentum as an extensive property, then our intensive property is velocity, similar to energy and angular momentum as mentioned over here. Now I move to my now my partner will Samir Akhtar will move take the slide further.
Okay, so here we will discuss the interpretation of the Reynolds transport theorem. So why do we need RTT? Well, RTT, as the definition says, it connects the extensive property of a system to the change of properties of control volume and the flux of passing of. So the for time rate of change of the property B of the system is equal to term 1 plus term 2, where term 1 is the time rate of change of properties of the control volume, and term 2 represents the net flux of properties out of the control volume by mass crossing the control surface. So why do we need hmm, why do we need Reynolds previous slide, please. uh, uh, One reason we need RTT is because it is very difficult to keep track of each fluid particle. So we use control volume approach instead of control system approach. Okay, next slide, please. So here we will discuss what to do when the control volume is moving. So for this, we have to see the whole situation from two places. First, we will see the control volume moving, uh, and the second case is we are moving with the control volume or we are sitting on the control volume. And then we will use the general equation where relative velocity is absolute velocity of the control volume minus absolute velocity. That's all. Now my partner will speak.
So yeah, after RTT, now coming on to the impact of jet. So here we are talking about how the fluid strikes, how the jet stream strikes different surfaces. Mm, good. So yeah, so basically we'll start with what is jet. Previous slide, please. Yeah. The jet stream is a liquid coming out from nozzle with a high velocity under a constant pressure. As you can see in the diagram, the jet stream, the nozzle is a that narrowing tube through which narrowing tube coming out from a pipe. The fluid is flowing through the jet. The impact of jet means the force exerted by the jet on a plate, which may be stationary or moving. The plate may be flat or curved. The force obtained from Newton's second law of motion impulse, which is also known as momentum principle. So now talking about impulse momentum theorem. The impulse momentum theorem states that the change in momentum of an object equals to the impulse applied to it. Uh, and by looking at the formula, we are using here force is equal to the derivation of the mass into velocity. Then we can here use the product rule, with respect to the time. We are differentiating velocity, m dv by dt plus v dm by dt. Uh, for constant mass, where we can put dm is equal to 0, the change in momentum may occur due to the change in magnitude of the velocity, or in its direction, or due to both. We can look at the expression f is equal to m dv by dt. There are different cases for the impact of jet. The force exerted by the jet on a plate will be considered in different methods. Like first, we are taking on a stationary plate when the stationary plate is just vertical to the jet, flat, or inclined to the jet, or it is a curved plate. The same cases we can take for the moving plate, the vertical plate and the inclined plate and the curved plate, where the plate is moving when the force of a jet of water applied to it. As you can see in the figures, the first figure is here is an example of a vertical plate which is at the rest or fixed, and the second example is of the inclined plate, where you can see the different different directions in which the fluid is flowing, and the third example is a moving curved plate, where different directions of fluid is moving at an angle. Force exerted by the jet on a vertical flat plate. When the plate is stationary, when the plate is fixed, it can't be moved, then we'll take the velocity as a v in the jet of the direction in the x direction, where then the jet is moving towards the plate. D is taken as a diameter of the jet, and the area is a jet of a nozzle, where it's taken as pi d square by 4. Next. So now consider a jet of water strikes a stationary vertical plate as shown in the figure in the previous slide. The jet after striking the plate will deflect through the 90-degree as the plate is vertical, we can see. So the final velocity of fluid in the direction of the jet after striking the plate will be 0. Because of the plate is vertical, the horizontal component of the jet is at 0, and the water strike will deflect in the perpendicular direction. So it will gain a velocity in vertical component only. So the force exerted by the jet on the plate in the direction of jet, we can calculate as rate of change of momentum in the direction of force, which we can take as initial momentum minus final momentum divided by time. So we can put the formula of momentum, which is mass into velocity. So for initial momentum, we can take the initial velocity, and final momentum, we can take final velocity divided by time. On dividing the whole, uh, so by taking mass is equal to rho into a velocity of the jet before striking and after striking, we can acquire a formula rho a v square, which will give us the rate of change of momentum in the direction of force striking on the plate. Next. So when we take up example of a vertical plate in a moving condition, so when the plate is moving, then we want to take a relative velocity, relative velocity of jet with respect to the plate, and initial velocity of the jet will we take as a u. We'll take the velocity of plate as u, and the velocity of jet we have taken already a v. So the relative velocity of jet with respect to the plate, we'll take it as v minus u. So the rate of change of momentum in the direction of the force, the formula will remain the same. We just have to consider the velocity of plate also. So it will become rho a v minus u whole square. So Fx is equal to the rate of change of momentum in the direction of force. So as we can see in this case, the work done by the jet on the plate is as the moving or stationary plate, where the work done is 0. Work done by the jet on a flat moving plate, it is work done per second. which is equal to force into the direction of the distance in the direction of force divided by time distance, which will come out to be rho a v minus u whole square into u. Yeah. So now I'll hand it over to Sanyam. Sanyam, you are on mute.
You have to
Okay.
unmute yourself.
Okay. So this is our third case when the plate is stationary and it is inclined. So we have to find the force exerted by the jet on this plate. As you know that the plate is inclined, so we have to take the component of the initial velocity of the jet. So initially, the velocity of the jet in the x direction is v, but we have to find the velocity which is perpendicular to this surface, which is, if this angle is theta, then this angle is theta, and when we take a component normal to it, it will be v sine theta. So uh, the mass striking the plate per second is rho av, and the angle between the jet and the plate is theta, that we already discussed. Now, uh, now to find the force exerted in the normal direction is basically just mass of water striking per second into initial velocity minus final velocity. So the mass striking per second is rho av, that we discussed earlier, and the initial velocity in the normal direction, the component of it normal to it, is v sine theta, and the final velocity is zero because the plate is fixed and water came at rest in the normal direction. That's why the final velocity is zero. So the force exerted by jet in normal direction is rho av square sine theta. Now to find its component Fn, we can find the component of Fn in x and y direction also. If we take the component in the x direction, so we can multiply it by cos 90 minus theta, which comes out to be sine theta. So the x component of Fn is Fn sine theta, and Fn sine theta, Fn is rho av square sine theta. So the whole term come out to be rho av square sine square theta. And similarly in the y direction, we multiply Fn with the cos theta. So our final component of Fn perpendicular to the flow is rho av square sine theta cos theta. So this is the similar case to the previous case, but the thing is the plate is now moving. To solve these type of questions, my other fellow mates explain this very well, how to solve these type of question when a control volume is moving. So as you know that this control volume, or you can say a plate, is moving with a velocity u in x direction. So if we sit on this plate, then the relative velocity of the jet will be v minus u. So the mass striking per second to the plate is actually rho a v minus u. As you can see, mass of the water striking the plate per second, rho a v minus u. This is the mass striking per unit per second. And similarly, in the previous slide, as you know that we have to take a normal component of that. In the previous case, we take a normal component of just v, but here we take a normal component of v minus u sine theta. So the normal component v minus u sine theta, and its final velocity is zero because the plate is the water comes at rest in the normal direction. So the final velocity is zero. So the force is rho a v minus u whole square sine theta. Now we can find its component in x and y direction by multiplying by sine theta and cos theta. So rho a v minus u whole square sine square theta is the x component, and y component is rho v minus u whole square sine theta cos theta is the perpendicular flow. And the work done, you can just multiply this fx with the velocity to find the work done. So this is another case when the nozzle, the jet is striking the curved plate. So the it is stationary. So we don't take a relative velocity. So the mass striking per second the plate is just rho AV, and we initially final velocity, as you can see, is in this direction with the angle theta, which is a blade angle at the outlet. So we take a component of it in the x direction, which is v cos theta. So the final velocity is opposite of that initial velocity, so we take a negative sign here. And so when we write impulse momentum equation to it, so it becomes v, which is the initial velocity, minus final velocity. Final velocity is opposite of that direction, so we take a minus. So minus minus becomes plus, so our force exerted by the jet in the x direction would be rho a v square 1 plus cos theta. So in this case, the velocity, the plate is moving with velocity v. In the previous case, as you can see, it is fixed. We are represented it by this symbol. But in this, the plate is moving with velocity v. So we know that when a control volume is moving with u, we sit on it and took a relative velocity. So the relative velocity would be v minus u, and the mass striking per second is rho av minus u. So rho a v minus u is the mass per second that strike the plate, and initially the velocity is v minus u. This is a relative velocity minus final velocity. Final velocity is make an angle theta with the x direction. So we take a component of it in the x direction, which is v minus u cos theta, which is opposite of the initial direction. So we took a minus here. So minus minus become plus, and it is very similar to previous case. Just in case of v, it is v minus u. U is the velocity of the plate. So v rho a v minus u square 1 plus cos theta is the force exerted by the jet in x direction, and multiplied by u gives us the work done per second, which is just power. And in that case, here we strike the plate at the center, but here the jet strikes the plate tangentially, it flow over it, so without shock. So here we simply take the direction of the initial velocity would be v cos theta, and the final velocity is in the opposite direction minus v cos theta, and the mass striking is rho av. So just putting it there, so minus minus become plus, and v comes out to be common, and 2 rho a v square cos theta is the force exerted by the jet in x direction of this plate. But there is a case when this plate becomes unsymmetrical. So it makes an angle theta and phi at the outlet and theta in the inlet. So it is similar to that case, but we here take the cos theta and cos phi, and it is similar to the previous case. Now my fellow friend Sarthak Khinchi will explain you about the next cases.
Here, like previous cases, we are moving the plate, but the plate is still unsymmetrical. So the conditions added are that the velocity of relative velocity of the jet should match the angle of blade at the inlet. So here, as it is given in the diagram, v1 is actual velocity of the jet, u1 is the velocity of blade, vr1 is the relative velocity of the jet with respect to the blade, vf1 is the vertical component of the vr1, and vw1 is the horizontal component of vr1. At the outlet, we see vr2, which is relative velocity of water, which is at the exit. v2 is the actual velocity that we can see at at rest. U2 is the velocity of the blade. VF2 is the vertical component of VR1, VR2, and VW2 is the horizontal component of VR2. Theta is the angle of the blade, as it is unsymmetrical. So we are taking two angles, theta and phi. Theta is the angle at the inlet, and phi is the outlet. Alpha is the angle made by the actual velocity of jet and the velocity of the blade, and beta is the actual angle between actual velocity of the water that can be seen at the exit and velocity of blade. Next slide. Here we have taken the assumption that, as before, we have taken the assumption that the blade is smooth, so VR1 and VR2 are equal, and as U is constant, so the U1 and U2 are equal. Force exerted by the jet in the direction of motion is equals to QV, that is mass of water striking per second, into initial velocity minus final velocity. Here we have taken as VR1 is the initial velocity relative to the blade at the inlet. We have taken the initial velocity as VR1 cos theta, and cos theta as we have taken the tangential component of it, and VR2 cos theta, same as before, we have taken the tangential component of it, and work done is force into velocity. Then we have multiplied, we have taken the force which we have then multiplied it by visual velocity. Here we have added some fixed blades to a wheel, and the jets, and we have taken some assumptions to it. Assumptions are that in this case the mass of water coming out from the nozzle per second is always in contact with the plates when all plates are considered. Mass of water per second striking the series of plate is PVA. The jet strikes a plate with the velocity V minus U. After striking the blade, the jet moves tangentially to the plate, hence the velocity component in the direction of motion of the plate is equal to 0. Here we have as before, we have found out the force, which is PAV into initial velocity, which is V minus U minus final velocity, that is 0. That is 0. Work done is force into velocity. Force we have taken out to be PVA across V minus U, and work done comes out to be PVAU into V minus U.
So this is all from our side, and I think you get a better understanding of the RTT theorem and the impact of jet concept. Thank you.